Equivalent systems are not a way of solving a problem, but rather a way of allowing the problem to have loading simplified, okay? So they are essentially equivalent loading systems, all right? So let's look at some of the steps that we can do in here, all right? So the first three steps that we would do for any determination of an equivalent system is to do the summation of the forces in X, summation of forces in Y, and then the summation of moments at a point of interest. Okay, so those first three need to be done, and then we can create in step 4 a free body diagram with the results. We could stop at this point if all we want is an equivalent system that has forces and moments, but if we want one that is just purely forces, we would then have to go on to step 5 where we draw a free body diagram, and we would move that force along the beam, okay, in this case we are just looking at beams, to create a moment that would then be represented only by forces. So let's look at this. So here we have a problem where we have a beam. I've simplified it, okay, and it has a load of 300, another load of 400 at a 60-degree angle. It also has a moment, okay, going in clockwise direction there, and 250 located 2 feet from the end of B. Our point of interest here is going to be A. So let's go ahead and we'll go through the first 3 steps here. So step 1 is the summation of forces in X, and we get 200. Step 2, summation of forces in Y, and we get minus 646.4. And then lastly, we do the summation of moments at point A, and we get minus 4,267.7. Okay, so now go ahead and pause the video and then rewrite or redraw this free body diagram with all the forces and moments represented at A. All right, so then this would be the equivalent system, okay? So let's look at that. So we have a force in the X direction here, okay? A force in the Y direction down, and then we have the moment here, also clockwise, all right? So this would be equivalent to this, okay? So it's a little bit more simplified, as you can see, and there's a reason for that, you know, that we do this. So now we could stop here if that's all we wanted. But now what we want to do is we want to just represent this in pure force, okay? And I have this this force resultant located here in F, okay? So what we want to do now is slide this force along this axis so that it creates that 4,267.7 moment here. And again, the moment here is clockwise. So if we slide the force to the right, it's going to be increasingly driving a moment there, which is force times distance. So whatever d over, okay, it's going to create it. Now, you'll notice that of the two here, the X and Y, only one of them creates a moment about A if we slide it, because the 200 is its line of action passes through A. So go ahead and pause the video, and using the formula, moment is equal to force times distance, determine how far down it needs to be to create this moment. All right, so here we go. We have a new free body diagram. I've indicated the distance d here. I'm just showing the x and y component in this case, and I'm using the moment is equal to force times distance. Solving for distance here, which is then moment over force. We have all those, and so we calculate that the distance from A that this force would have to be would be 6.6 feet. And so this force, these two forces, okay, which could be represented as one force too at an angle, is equivalent to the original, okay?